This video is introduction to omnidirectional vision system. Firstly, let's consider what the goal of the computer vision. So, for example, we have image, how the people understand the world, and here how the computer understands the image. So we can understand what elements on a scene present, and computer see just numbers of the image. So by these numbers, computer has to understand the image and the world. So this is the goal. And scene understanding. The goal of the computer vision is to understand the world as humans do. The human vision perceive 120 degrees horizontal field of view without eyes movement. With the eyes movement, it's even more. Human vision is able to provide the 3D understanding of the scene as well. So we can conclude that human vision perception must have a wide field of view and also understand the depth of the scene. So consequently, the reduced field of view or the lack of the depth information limits the goal of developing intelligent system to match the performance and robustness of human vision. So we observed that ultra-wide angle lenses, for example fish eye lenses, can be beneficial for different tasks. This is not surprising since the 180 degrees field of view allows to include much more details about the scene. However, just by using a snapshot captured by a system including one camera, we cannot get the depth information, so we need to consider also other details to understand the depth. For example, here we have a comparison of the depth. Here is a standard camera with a standard field of view, and here is the wide angle lens, so we can see that more elements now cover our image. And here also snapshot from the upper view, also the standard field of view and the large field of view, wide field of view. So how to understand the depth? For example, we can add a laser information to our computer vision system. So here we have the camera, below we have the laser emitter, and we project it to the world. Next, this laser intersect obstacles, and we can estimate distance from camera to this laser and means to the obstacle as well. So how we do it, we extract laser from the belonging obstacle, and we work with this laser, we proceed it, and we get the depth information. So when we proceed the image, we will get the distance to the left wall, right door, left door. So let's consider the math relationship between the camera and laser. So how these coordinates are related. So for example, we need to understand what's the distance between the camera and laser. So here's the origin of camera with the coordinates x1, y1, z1. Here's the coordinates of the laser. So they are related just with the offset along x-axis, y-axis, and z-axis. And also we can write it in a matrix form this way. And if we multiply these matrices, we will get the similar result. So we can write it just as a usual equation or in a matrix form. Computer vision systems usually works with a matrix form because it's more easy for computer to do a mathematical operation with the matrices. And also here maybe rotation part present. So here we only consider the offset, and here also we must to consider the rotation part. So here example with two vectors, how they related through the rotation. And if we have rotation around different axes, for example around z, x, y axis, next how we need to do the order, it makes sense because firstly we need to put here rotation matrix of the z-axis, next y and x. If we change this order, then we won't get a similar result. For example, if first it will be rx, if we change this order, we will get a different result. So this order is very important. So when we include this part to our transformation matrix, so it will have a rotation matrix part and also the offset. So now this is the relationship between these two systems. Also here let's consider firstly the simple camera model, the relationship between world coordinates and image coordinates. So here we have our lens, here is the world, similar to this. Here just shown the pinhole camera model. If we take a simple box, make a hole here, then if we take a look inside, we will see the projection in a reversed way. So here is also a pinhole camera model. Here world coordinates, here the image coordinates, and using simple geometry we can write a relationship between them. For example, we consider these similar triangles, and the relationship we can divide u by x. It will be similar if we divide f by z. And from here we can, for example, find u. U will be equal to fx divided by z. Similar for the v, also from the similar triangles. And again we can write it in a matrix form. So pixel coordinates, world coordinates, how they relate. So again, if we multiply these two matrices, we will get a similar equation. So firstly we got them from similar triangles, and next we put them to the matrix form. And also here we need to take into consideration the center of the image. So here the projection, it goes through the center, so here we need to take it also to the consideration. If we just consider 0 here, the pixels 0, 0 corresponds to this point. Next it increases along this axis, and the center it will be here, and it's not the coordinates 0, 0. It will have some value. So to our equation we need to add it here and also in matrix form here. Next, how can we estimate the distance? For example, the distance between camera and laser is known to us, and we need to estimate distance from camera to obstacle. For example, also this image. So this distance is known to us. So this part is known to us, and we want to find distance from our camera to the wall. So this distance we want to find. So we also can find it from the geometry. Again, our camera model, our equations, and from these equations, so this ZL we want to find. So from this equation we can write the ZL, and all this data is known to us. So only this one is unknown. F, Y we know, it's we can know it from the intrinsic camera parameters, from the calibration. YL is this distance. For example, we measure it we measure it, this distance between camera and laser, by the ruler, and this pixel coordinates also is known to us. So this pixel coordinates also will be known to us from the image. So we know it where it's on the image, similar where it was here, so we know this pixel coordinates of the laser. So every pixel we project to the world system. So that's how was it with a simple pinhole camera. Also, now let's consider the fisheye image with a wild field. Again, example, here is a simple image with a simple camera, and here is a wide angle lens, so it includes more details to the scene. For example, this car, we didn't see it here, now we can see this car. And let's consider this firstly. Also, it's important to carry out the calibration of the vision system. For example, if we don't consider orientation of the vision system, if we only consider the distance between camera and laser and don't consider the rotation part, we may get a not accurate result. So in calibration case, we need to consider the camera rotation matrix, because here it was an assumption that camera is parallel to the floor, but in real cases the camera cannot be parallel to the floor. It also has a rotation matrix. Also, the transformation matrix of the laser plane also have the orientation. So also we need to consider it during the calibration. And here, yes, we now deal with the wide angle lens. Here the camera model a bit different. So here we have the polynomial, this part, it presents the shape of the lens itself. So now it's different shape, so it's presented by this polynomial. Also, in this example, it was considered the several laser planes, and in order to make a calibration, the vision system must not include several laser emitters with the same emitting color, for example, red color. We can only calibrate one laser plane emitted by one laser emitter. So it's important to include not several, but only one laser emitter. So like this one. Also it can cover all elements in a scene, but just with one laser emitter. Again, here in general form, the equation of the laser plane projection can be written in a following way: camera rotation matrix, transformation matrix of the laser plane. It consists of rotation matrix of laser and translation part. This one is a distance between camera and laser plane. Here this part, pixel coordinates, column vector of camera rotation matrix, parameters. These parameters present column vectors of laser plane transformation matrix, and these are world coordinates of the laser projection. And this is a polynomial to represent the shape of our lens. So this is a fisheye camera. This is the laser, and this is a snapshot including these two elements. So why the calibration is important? Let's consider again. For example, if we don't take calibration into consideration, we will not get accurate map. Also here, for example, it has the beta shape. It reminds us of the structure of this environment, but still it also has rotation, so it's also not really correct. So this one is a correct one. So here we have structure similar to this left wall, front wall, right wall, and our system here. So now let's consider how to get distances, how to calculate world coordinates from this matrix. And firstly we need to simplify this equation. So the laser plane is located on the constant from the camera distance. It's this distance. So x, y, z, and the distance between camera and laser plane is the z-axis. So we are interested in this T3. We are not interested in T1, T2, so these two are zeros. So now if we try to make a multiplication of these parameters, also y here is 0 because the distance between camera and laser is constant. So when we work with the 3D world, here these coordinates to the obstacles, they change only in x and y direction. So here x, here is y, and distance between camera and laser is known to us. So we know this distance, and this is constant. So that's why, and this is equal to T3 constant, and it's equal to T3. So that's why we only interested in x, y, and here z is 0 because it's equal to T3. So here this one is not changing, so that's why it's here 0. Now if we do multiplication between these two matrices, so how we do this multiplication, we simply, so this part we multiply here. So when it will be the R11 will be multiplied by x, next R12 will be multiplied by y, and when it goes to R13 it will be multiplied by 0, so it will be 0. Also similar here, this one will be multiplied by x, this one by y, this one by 0 also will be 0. Next R31 by x, this one by y, and this one again 0. So also it's written here, so these coordinates became 0, so we can remove this column, it will be 0. So these parts are 0, we're not interested in here. So finally from here we go to this equation, and here we already multiplied this matrix by this matrix. So and we just got this 3 by 3 matrix, homography matrix. So these two we combined. So these two we combined and we got this matrix. So and here this one. So next how we next again multiply this one by this one again. Again we go from here to here, so hy1 by x, plus h12 by y and h13 by 1 just h13. Similar with the second row and third row. So, and next we have the cross product here. Here is the example how the cross product can be calculated. For example, here, firstly we take a2 multiplied by b3 minus a3 multiplied by b2. So similar to this example, we do it for our matrix. So if we take a look at here, so firstly we take a2, this one, so we need to multiply v by b3, this one. So we multiply v by this one. So similar is here. Next it's minus a3 minus a3 multiplied it by a3 multiplied by b2 multiplied by this value. So similar here. So once we finish with this, next we multiply a2. Next we multiply a3 by b1. a3 is this one, b1 is this one. So similar here. Minus a1 multiplied by b3 and the last one we take a1 it's u multiplied by b2 this and this minus v multiplied by b1 this one. So that's how we made a cross product here. Next we consider only these two last two equations. So we want to find x and y from them. Here we consider last two equations, so only these two, and we don't take into consideration the first one. Just consider these two, and we open brackets. So we multiply every element by f row, and here we multiply every element by u. Here we multiply every element by u. Here multiply everyone by v. So we open bracket, and next we can separate x and y. So here we search for every element which has x. So for example, x is here, x is here, so we have these two elements here. Next we search for y, so we separate this part on this part, so that's what we have inside brackets, and these separate elements plus minus this element. Similar for this equation, we also separate x and y and the rest elements. And here, in order to do not deal with huge equation, we define new variables. For example, this one will be a1, so we just wanna simplify our equation. So in order to do not write currently here, we will just write here a1. Second one is this one. We will not write this, we will write here b1, and this one will be c1, and similar here, it will be a2, it will be b2, and this one will be c2. So we just find x, y, and next we replace the values back again. So once we simplified our equation, we have here the simplified equation. And from here we can, from the first equation, for example, we can write x. So we move these two to the right side and divide it by a1. So it's how we found x from the first equation. And next in second equation we replace, make a replacement by this value, and from the second equation, after multiplying everything, we will have also by a1 we will have this part. So firstly so here instead of x we put here also multiply everything by a1, and we will have this equation after replacement. From here we separate x, we separate y, and we find y. So divide this by this. And so now we know x and y. Thus each world coordinate of the laser projection is represented by distance from the camera to the laser plane, and these two coordinates x and y. So once we found them, we can make a replacement back, put this back to our equation and calculate x and y. So that's all. Thank you.